Sagittarius A star. You are staring at a computer screen in the basement of the Max Planck Institute for Extraterrestrial Physics in Garching, Germany. It's 3:27 in the morning on May 15th, 2002. The data stream from the Very Large Telescope in Chile fills your monitor. Infrared signatures, stellar positions, velocity measurements. You've been tracking the same star for 8 years. STU, they call it. A blue giant racing around something invisible at the center of our galaxy. The numbers don't make sense. They never have. 25 million kilometers per hour, faster than anything should move and survive. The star completes one orbit every 16 years. It swings within 120 astronomical units of something that shouldn't exist. Something with the mass of 4 million suns compressed into a space smaller than Mercury's orbit. The gravitational forces should have shredded STU into plasma clouds decades ago. Instead, it accelerates. For 26,000 light years, we've been living above a monster. The European Southern Observatory's Very Large Telescope Array has been monitoring Sagittarius A star since 1992. Dr. Reinhard Genzel of the Max Planck Institute and Dr. Andrea Ghez of the University of California, Los Angeles, independently confirmed what infrared astronomy had been whispering for decades. The galactic center harbors a supermassive black hole with a mass of 4.1 million solar masses. Their work, published in the Astrophysical Journal in 2008 and refined through continuous observation campaigns, earned them the Nobel Prize in Physics in 2020. The stellar orbits around Sagittarius A star follow Kepler's laws with terrifying precision. Star STU, a main sequence B-type star with roughly 15 solar masses, maintains an elliptical orbit that brings it within 120 astronomical units of the event horizon at perihelion. During its closest approach in 2018, the star reached velocities exceeding 7,650 kilometers per second, nearly 3% of the speed of light. The Keck Observatory and the Very Large Telescope recorded gravitational redshift effects exactly as Einstein's general relativity predicted. The star's light stretched toward longer wavelengths as it climbed out of the black hole's gravitational well. But here's what makes this impossible. Tidal forces at such proximity should have disrupted STU millions of years ago. The difference in gravitational pull between the star's near side and far side, what astrophysicists call the tidal gradient, should generate internal stresses exceeding the star's structural integrity. At 120 astronomical units from a 4 million solar mass black hole, tidal forces reach approximately 10 to the power of minus 4 meters per second squared per meter. For a star 15 times the mass of our Sun, this should have triggered catastrophic mass loss or complete stellar disruption within the first few orbital periods. The standard cosmological model says that S2 represents a young star, recently formed from gas clouds in the galactic center's star-forming regions. Its high mass and blue spectral classification suggests an age of only 10 to 15 million years. The black hole's accretion disk could have provided the dense molecular material necessary for rapid stellar formation in such a hostile environment. Once formed, the star became gravitationally bound to Sagittarius A star, settling into its current highly elliptical orbit through gravitational interactions with other stellar objects in the nuclear star cluster. But the observational data doesn't support this timeline. Stellar evolution models indicate that a 15 solar mass B-type star should consume its hydrogen fuel and evolve off the main sequence within 10 to 20 million years. Yet STU shows no signs of approaching the end of its main sequence lifetime. Its spectrum remains consistent with a young, hydrogen-burning star, despite existing in an environment where star formation should be nearly impossible due to the black hole's tidal disruption of molecular clouds. Some astrophysicists suggest that STU migrated inward from the galactic disk through a process called dynamical friction. But this mechanism requires timescales longer than the star's expected lifetime. The most disturbing aspect involves the other stars. STU is not alone. The galactic center hosts an entire population of massive stars in similarly extreme orbits. Starstone disappeared from observations in the 1990s, likely after crossing the event horizon. Star S14 maintains an orbit that brings it within 700 astronomical units of Sagittarius A star. Star S47 completes its orbit in just 18 years. Each of these objects defies the basic physics of stellar survival in such extreme gravitational environments. Recent observations from the Event Horizon Telescope collaboration have revealed that Sagittarius A star exhibits periods of rapid flaring, increasing its luminosity by factors of 100 within minutes. During these events, the surrounding stars experience radiation doses equivalent to standing 1 kilometer from a hydrogen bomb detonation. Yet they continue their orbital dance, unchanged and unperturbed. How does a star maintain structural integrity while experiencing tidal forces that should tear it apart? What mechanism prevents the gravitational disruption that stellar physics demands? Why do these massive stars exist in a region where star formation should be impossible? How many more stellar ghosts orbit beyond our current detection limits? What happens to the stars that don't survive their dance with darkness? But if a black hole with 4 million solar masses can harbor such mysteries, what secrets hide within objects 1,000 times more massive? Ton 618. You are calibrating the European Southern Observatory's Very Large Telescope in Chile's Atacama Desert when the spectral analysis arrives from the Wide Field Infrared Survey Explorer mission data. March 2018. The numbers on your screen defy immediate comprehension. The redshift measurement reads 0.37. This quasar sits 11 billion light-years from Earth. Its light traveling toward us since the universe was barely 2.5 billion years old. But that distance isn't what stops your breathing. It's the luminosity calculation. This single object radiates energy equivalent to 140 trillion suns every second. The Astrophysical Journal published the mass calculations in 2019. TON 618 contains the gravitational equivalent of 66 billion solar masses compressed into a region smaller than our solar system. To comprehend this scale, consider that our own Milky Way's central black hole, Sagittarius A star, weighs 4 million solar masses. TO 618 outweighs it by a factor of 16,500. If you place this monster at the center of our galaxy, its event horizon would extend past Neptune's orbit. The accretion disk surrounding TON 618 burns at temperatures exceeding 100,000 Kelvin. Plasma spirals inward at velocities approaching 30,000 kilometers per second. The magnetic fields generated by this infalling matter exceed Earth's magnetic field by factors measured in billions. The jets of relativistic particles shooting from its poles stretch across 400,000 light-years of space, wider than the entire diameter of our local group of galaxies. Here's what makes this impossible. TON 618 is consuming matter at a rate that violates every model we have for black hole growth. The object devours mass equivalent to our entire planet every 6 minutes. That's 10 Earth masses every hour, 240 Earth masses every day. The Eddington limit defines the maximum rate at which any black hole can accrete matter before radiation pressure from the heating material pushes new material away. TON 618 exceeds its theoretical Eddington limit by factors that shouldn't allow it to exist. The standard cosmological model says supermassive black holes grow through 2 primary mechanisms. They begin as stellar mass black holes formed from collapsed stars, then gradually accumulate matter over billions of years. Alternatively, they form from the direct collapse of massive gas clouds in the early universe, creating intermediate mass seeds that grow through mergers and accretion. Both processes require enormous amounts of time. For TON 618 to reach 66 billion solar masses within the universe's current age requires accretion rates that theory suggests are physically impossible. But the observational data from the Sloan Digital Sky Survey and subsequent follow-up observations by the Keck Observatory confirm these measurements. The mass estimate comes from analyzing the orbital velocities of gas clouds near the black hole's event horizon, measured through Doppler shift analysis of emission lines. The luminosity calculations derive from multi-wavelength observations spanning radio, infrared, optical, and X-ray frequencies. Independent research teams using different telescopes and methodologies have confirmed these numbers repeatedly. Some astrophysicists suggest TON 618 formed through exotic mechanisms in the early universe. Primordial black holes created from density fluctuations in the first moments after the Big Bang might have provided massive seeds. Others propose that supermassive stars, hundreds of times more massive than anything that exists today, collapse directly into black holes without the intermediate neutron star phase. A few theoretical models invoke modifications to general relativity itself, suggesting that gravity behaves differently at these extreme scales and densities. The feeding rate presents another puzzle. Current models predict that black holes this massive should have cleared their surrounding material long ago, entering a quiescent phase with minimal accretion. Instead, TON 618 continues its violent consumption, suggesting either an inexhaustible supply of infalling material or feeding mechanisms that operate outside our current understanding of accretion physics. The jets emerging from its poles carry energy equivalent to the total power output of millions of galaxies, yet the black hole maintains this output across cosmic timescales. Recent observations from the James Webb Space Telescope have identified dozens of similar ultramassive black holes in the early universe, each one challenging the maximum theoretical mass limits for black hole formation. These objects exist when the universe was less than 1 billion years old, leaving insufficient time for conventional growth mechanisms to produce such monsters. How does a black hole achieve a mass that theoretical physics suggests is impossible? What feeding mechanisms allow it to exceed the Eddington limit by such enormous factors? Why do we find multiple examples of these objects when models predict they shouldn't exist at all? Could the presence of ultramassive black holes in the early universe require fundamental revisions to our understanding of gravity itself? The universe's first gravitational wave detection would soon reveal that even our models for how black holes behave when they collide might be dangerously incomplete. GW 150914. You are staring at a computer screen in Hanford, Washington, September 14th, 2015, 4:09 in the morning, Pacific Daylight Time. The Laser Interferometer Gravitational Wave Observatory Detector has just registered something impossible. 2 laser beams, each traveling 4 kilometers down perpendicular arms, have been compressed and stretched by less than 1/10,000th the width of a proton. The pattern on your screen shows a distinctive chirp, a frequency that rises from 35 Hz to 250 Hz in 0.2 of a second, then silence. 3,000 kilometers away, the identical detector in Livingston, Louisiana, recorded the same signal 7 milliseconds later. What you are looking at is the death scream of 2 black holes. The Laser Interferometer Gravitational Wave Observatory collaboration, led by physicists Kip Thorne, Rainer Weiss, and Barry Barish, had been searching for gravitational waves for decades. The detection represented the culmination of 40 years of technological development and more than $1 billion in funding from the National Science Foundation. The signal, designated GW 150914, was analyzed by over 1,000 scientists across 15 countries and published in Physical Review Letters in February 2016. The data revealed something that should not be possible. 2 black holes, 36 and 29 times the mass of our Sun, had been spiraling toward each other for millions of years. In the final moments before merger, they were orbiting at 30% the speed of light. When they collided, they converted 3 solar masses of matter into pure gravitational wave energy in less than 1 second. Here's what makes this impossible. The merger released more power in gravitational waves than all the stars in the observable universe produce in visible light. For 0.2 of a second, this single event outshone every galaxy, every quasar, every stellar nursery, every supernova in the entire cosmos. Not in light, in the fabric of space-time itself. The energy output peaked at 3.6 times 10 to the 56th watts. To put this in perspective, the entire Sun produces 3.8 times 10 to the 26th watts. The collision generated 136 million times more power than the Sun will produce in its entire 10 billion year lifetime. This happened in the time it takes you to blink. The standard cosmological model says black hole mergers are rare but expected events. Einstein's general relativity predicts that accelerating masses should produce ripples in spacetime. When massive objects like black holes spiral into each other, they should radiate gravitational waves, losing energy and eventually merging. The mathematics work perfectly. The energy calculations are precise. Binary black hole systems should exist, evolve, and merge exactly as observed. But the standard model cannot explain how two black holes this massive formed in the first place. Stars 36 times the mass of the sun should not be able to collapse into black holes. They should explode as pair instability supernovas, completely destroying themselves and leaving nothing behind. The stellar evolution models show that stars between 25 and 130 solar masses undergo runaway nuclear reactions that tear them apart before a black hole can form. Some astrophysicists suggest these black holes formed through different mechanisms. Perhaps they were primordial black holes, created in the first moments after the Big Bang, when density fluctuations in the early universe collapsed directly into black holes without ever becoming stars. Perhaps they formed from the collapse of the first generation of stars, which contained no heavy elements and could grow more massive before exploding. Perhaps they grew through repeated mergers, starting smaller and accumulating mass over billions of years. The alternative explanations raise deeper questions. If primordial black holes exist, they would represent a completely unknown component of the early universe. If the first stars were fundamentally different from modern stars, our understanding of stellar evolution is incomplete. If black holes commonly merge and grow, the universe should be filled with gravitational wave signals we have not yet detected. The merger took place 1.3 billion years ago. The gravitational waves traveled through space for 1.3 billion years, stretching and compressing every atom they passed through by amounts smaller than subatomic particles. When they reached Earth, they were detected by instruments sensitive enough to measure changes in distance, equivalent to measuring the distance to the nearest star to the precision of the width of a human hair. What other cataclysms are rippling toward us through the darkness? How many black holes are locked in death spirals we cannot see? If two objects this massive can collide and release more energy than entire galaxies produce, what happens when even larger black holes merge? What happens when the supermassive black holes at the centers of galaxies eventually find each other? But perhaps the most unsettling discovery lies not in distant space, but in the center of our neighboring galaxy, where something is moving at speeds that should be impossible. M87 star. You are staring at a computer screen in the control room of the Event Horizon Telescope collaboration. It's April 10th, 2019. The image loads pixel by pixel, a golden ring of light surrounding absolute darkness, the first photograph of a black hole. But your eyes drift to something else in the frame, a narrow beam of light extending from the ring's edge. It stretches across your monitor, then across multiple monitors. The scale hits you. This jet of plasma extends 5,000 light years from its source, moving at 99.5% the speed of light. The supermassive black hole at the center of Messier 87 sits 55 million light years away in the constellation Virgo, 6.5 billion times the mass of our sun. The Event Horizon Telescope, a global network of radio observatories synchronized to create an Earth-size interferometer, captured this image after years of coordinated observations. Katie Booman at the Massachusetts Institute of Technology and Dr. Shepard Doleman at Harvard developed the algorithms that transformed petabytes of radio data into visible light. The image appeared simultaneously in 6 papers published in the astrophysical journal Letters. But the photograph revealed something that challenges our understanding of cosmic mechanics. The jet emerging from M87's black hole maintains its coherent structure across distances that dwarf our solar system, 5,000 light years. To put this in perspective, if you place this jet starting at Earth, it would extend past the nearest star systems, past the local bubble, deep into the spiral arm of our galaxy. The plasma within this jet travels at 299 million meters per second, just 1.5 million meters per second slower than light itself. Here's what makes this impossible. Nothing should maintain such velocity across such distance. The jet contains charged particles, electrons, protons, heavy ions, all moving in near perfect alignment. At these speeds, relativistic effects dominate, time dilates, mass increases. The energy required to accelerate matter to 99.5% light speed approaches infinity. Yet somehow, the black hole not only achieves this acceleration, but sustains it across thousands of light years of space. The Hubble Space Telescope has tracked this jet for over 2 decades. Images from 1995 show the same coherent beam. Images from 2020 show the same structure. Eileen Meyer at the University of Maryland published research in the Astrophysical Journal documenting superluminal motion within the jet apparent faster-than-light movement caused by the plasma's trajectory, nearly aligned with our line of sight. The jet maintains its narrow focus across cosmic distances where any normal beam of particles would disperse within light years. The standard cosmological model says jets form through magnetic field interactions near the black hole's event horizon. Matter falling into the black hole creates an accretion disk. This disk generates powerful magnetic fields that channel some material away from the black hole before it crosses the event horizon. The rotation of the black hole frame dragging winds these magnetic field lines into tight helixes that accelerate particles to extreme velocities. Computer simulations by Dr. Alexander Chekhovskoy at Northwestern University show how these magnetohydrodynamic processes can theoretically produce jets. But the mainstream explanation cannot account for the jet's sustained coherence. Magnetic fields weaken with distance. The inverse square law governs electromagnetic forces, just as it governs gravity. A magnetic field strong enough to confine plasma near the black hole should dissipate to negligible strength within hundreds of light years. Yet M87's jet remains collimated across 5,000 light years. The plasma beam is narrower at its terminus than at its origin, the opposite of what physics predicts. Some astrophysicists suggest the jet taps directly into the rotational energy of the black hole itself through the Blandford-Znaeck mechanism. Roger Blandford at Stanford University proposed that magnetic field lines threading the ergosphere, the region outside the event horizon where space-time itself rotates, can extract energy from the black hole's spin. This mechanism could theoretically power jets for millions of years. Others propose that dark matter interactions provide the missing energy source, creating invisible scaffolding that guides the jet across galactic distances. Radio observations from the Very Long Baseline Array show knots of plasma moving along the jet at apparent superluminal speeds. Motoki Kino at Kogakuin University documented plasma features traveling at 7 times the speed of light, an optical illusion created by their actual velocity of 99.9% light speed aimed nearly directly toward Earth. The energy density within these plasma knots exceeds that found in the cores of active stars. What mechanism sustains such extreme physics across cosmic distances? How does a black hole, an object defined by its inability to let anything escape, launch material at near light speed with surgical precision? Why does the jet maintain its structure where all known physics says it should dissipate? What invisible architecture guides plasma across thousands of light years without deviation? How does M87 convert gravitational collapse into the universe's most powerful particle accelerator? But M87 represents only one manifestation of black hole extremes, and not all cosmic accelerators announce themselves with such visible grandeur. XTEJ1550564. You are monitoring the data stream from the Rossi X-ray Timing Explorer as it locks onto a stellar mass black hole 20,000 light-years away in the constellation Norma. The year is 1998. Your instruments are detecting X-ray emissions, pulsing with a frequency that makes you check the calibration twice. The readout shows oscillations at 1,037 Hz, 1,037 complete rotations every second. You are watching space-time being dragged around a spinning void at velocities that approach the theoretical limits of what reality can sustain. The Rossi X-ray Timing Explorer, launched by the National Aeronautics and Space Administration in 1995, was designed specifically to study the timing properties of cosmic X-ray sources with unprecedented precision. When it turned its instruments toward XTEJ15505 564, during its 1998 outburst, the satellite detected quasi-periodic oscillations in the X-ray emissions that revealed something extraordinary about this stellar mass black hole. The oscillations, analyzed by teams led by researchers including Michiel van der Klees at the University of Amsterdam and published in the Astrophysical Journal Letters, indicated a spin rate approaching 98% of the theoretical maximum possible for a black hole. This is not simply fast. This is a stellar mass black hole, roughly 10 times the mass of our Sun, compressed into a region smaller than Manhattan, spinning at a rate where the fabric of space-time itself is being twisted into a relativistic hurricane. At 1,037 rotations per second, the ergosphere surrounding this black hole extends outward nearly to its event horizon. Inside this region, space-time itself is being dragged around with such violence that nothing, not even light, can remain stationary relative to a distant observer. The entire local geometry of reality is being wound up like a spring approaching its breaking point. The European Space Agency's XMM Newton Observatory and the National Aeronautics and Space Administration's Chandra X-ray Observatory have since confirmed these measurements through independent observations of the iron emission lines in XTE J1550, 564's accretion disk. The Doppler broadening of these lines, caused by matter orbiting at significant fractions of light speed near the black hole's event horizon, provides a direct measurement of the black hole's spin. The data consistently shows a dimensionless spin parameter of approximately 0.98, placing this object tantalizingly close to the theoretical maximum of 1.0. Here's what makes this impossible to fully comprehend. At spin rates approaching the theoretical maximum, the black hole's event horizon shrinks toward the so-called inner light ring, where the curvature of space-time becomes so extreme that stable orbits cease to exist. Matter spiraling inward experiences gravitational forces millions of times stronger than anything on Earth, heated to temperatures exceeding 100 million Kelvin before crossing the event horizon. The rotational energy stored in such a rapidly spinning black hole contains more power than our Sun will produce over its entire 10 billion year lifetime. The standard cosmological model says that stellar mass black holes form from the collapse of massive stars, and that their spin rates are determined by the angular momentum of their progenitor stars and subsequent accretion history. Computer simulations suggest that black holes can approach maximum spin through sustained periods of accretion, where infalling matter gradually spins up the black hole while adding mass. The process should be self-limiting. As the black hole spins faster, it becomes increasingly difficult for matter to fall in, preventing runaway acceleration. But the extreme spin rate of XTE J1550 564 pushes against the boundaries of what these models can easily explain. The black hole would need to have maintained steady, aligned accretion for millions of years to reach such velocities, requiring conditions that may be rare in stellar evolution. Some astrophysicists suggest that this black hole may have formed through alternative mechanisms, perhaps from the merger of two smaller black holes, or from direct collapse scenarios that preserve more angular momentum than traditional stellar collapse models predict. Others propose that we are witnessing a black hole that has been spun up by a companion star in a way that maximizes efficiency, approaching the theoretical limits through perfect astrophysical engineering. The Laser Interferometer Gravitational Wave Observatory has detected gravitational waves from merging black holes with high spins, suggesting that rapidly rotating black holes may be more common than previously thought. But XTE J1550 564 represents something approaching the absolute limit, a stellar mass black hole spinning so fast that it tests our understanding of how much angular momentum space-time can sustain. What happens to space-time geometry when a black hole approaches maximum spin? How close can reality come to the theoretical breaking point before something fundamental changes? Could there be stellar mass black holes spinning even faster, existing in states our current physics cannot describe? Is XTE J1550 564 an outlier, or a glimpse into the true extremes that gravity can achieve. Some stellar mass black holes, however, do more than test the limits of spin they tear apart and consume entire stars with a violence that announces itself across cosmic distances. Swift J 1644 plus 57. You're monitoring the gamma-ray sky from orbit aboard the Neil Gehrels Swift Observatory, March 28, 2011. The Burst Alert Telescope triggers. Coordinates lock. 14 hours, 44 minutes, right ascension, 57 degrees declination. The signal is screaming across 2.7 billion light-years of space. It's been traveling since before complex life existed on Earth. The gamma-ray flux is off the charts. This isn't a typical gamma-ray burst. Those fade in seconds, maybe minutes. This one keeps going. Hour after hour, day after day, month after month. The universe has just shown you something that shouldn't be possible. The Swift gamma-ray burst mission detected the initial outburst from Swift J 1644 plus 57 inches, the constellation Draco, on March 28, 2011. Within hours, ground-based telescopes, including the William Herschel Telescope in the Canary Islands and the Palomar Observatory in California, confirmed optical and radio counterparts. The Japan Aerospace Exploration Agency's Monitor of All Sky X-ray Image mission recorded simultaneous X-ray emissions. Joshua Bloom of the University of California, Berkeley, and his team published their analysis in Science magazine in 2011, identifying this as the first directly observed stellar tidal disruption event by a supermassive black hole. The numbers define the impossibility. The gamma-ray luminosity peaked at 10 to the 45th ergs per second. That's more energy than our sun produces in 10 million years, released every single second. The relativistic jet extended outward at 99.5% the speed of light. Temperature measurements from the Spitzer Space Telescope indicated the debris disk reached 15,000 Kelvin. The European Southern Observatory's Very Large Telescope in Chile measured the host galaxy's redshift at 0.354, confirming the source lay 2.7 billion light-years away. Most impossibly, the emission continued for over 2 years. Gamma-ray bursts don't do this. Here's what the observations reveal. A star, roughly the mass of our sun, wandered too close to a supermassive black hole containing several million solar masses. The black hole's tidal forces, stronger than the star's own gravity, ripped the stellar material apart. Half the debris fell into the black hole, forming an accretion disk. The other half was ejected in a relativistic jet aimed directly at Earth. The process converted stellar mass into pure energy with devastating efficiency. The European Space Agency's XMM Newton Observatory tracked the temperature evolution as the accretion disk cooled over months, exactly matching theoretical predictions for stellar disruption. The standard cosmological model says tidal disruption events should produce brief, intense flares as stellar material spirals into supermassive black holes. Computer simulations by Dr. Tzvi Piran at the Hebrew University of Jerusalem predict these events should peak within days and fade within weeks. The energy output should follow predictable patterns as the debris settles into stable orbits or falls past the event horizon. Most events should be too distant and too brief for detailed study. Swift J 1644 plus 57 fits these parameters perfectly for the first few months, but the sustained emission challenges every model. The jet remained active for over 700 days. The Harvard-Smithsonian Center for Astrophysics Analysis showed the gamma-ray flux varied by factors of 10 on timescales of hours, indicating ongoing instabilities in the accretion process. The National Radio Astronomy Observatory's Very Large Array detected radio emissions that strengthened over months, suggesting the jet was interacting with surrounding material in ways not predicted by simulations. Most troubling, the Fermi Gamma-Ray Space Telescope recorded high-energy photons, continuing to arrive 2 years after the initial detection, long after all theoretical models predicted silence. Some astrophysicists suggest the black hole was rotating at near maximum speed, extracting additional energy from space-time itself through the Penrose process. Others propose the stellar remnant contained unusual magnetic field configurations that sustain the jet beyond normal timescales. Andrew McFadyen at New York University has modeled scenarios where multiple stellar encounters occurred simultaneously, feeding material into the black hole over extended periods. None of these explanations fully account for the observed duration and energy output. The Deep Space Network tracked the signal's evolution across multiple wavelengths for over 800 days. Every measurement confirmed the impossible, a stellar death that refused to end. The debris should have either fallen into the black hole or been ejected into space within months. Instead, Swift-J 1644 plus 57 continued broadcasting its destruction across billions of light years, visible to every gamma-ray telescope in Earth's vicinity. What keeps a stellar disruption active for years, beyond all predictions? How does a black hole sustain relativistic jet emission long after the stellar material should be consumed? Why did this particular star's death announcement echo across the cosmos for so long? If tidal disruption events can maintain such extended activity, how many stellar deaths are we missing in distant galaxies? How many black holes are feeding on invisible stellar debris right now? The universe contains stellar violence that exceeds our models, and some black holes demonstrate feeding behaviors we have yet to understand. Maxi J 1820 plus 070. You are monitoring the all-sky X-ray image detector aboard the International Space Station when the alert comes through at 14 minutes past midnight, Greenwich Mean Time, on March 11th, 2018. The automated system has detected something impossible in the constellation Ophiuchus. A stellar mass black hole is accelerating plasma to temperatures that should not exist in nature, while simultaneously launching twin jets of matter at nearly the speed of light with mechanical precision that defies every model of chaotic accretion physics you know. The monitor of all-sky X-ray image telescope had discovered Maxi J1820 plus 070, a black hole system 8,000 light-years from Earth, where something was violating the fundamental relationship between gravity, thermodynamics, and relativistic mechanics. Within hours, observatories across the globe were tracking this system as it entered an outburst phase that would challenge our understanding of how matter behaves under the most extreme conditions in the universe. The European Space Agency's XMM Newton X-ray Observatory recorded the corona temperatures 1 billion Kelvin. To understand this number, consider that the core of our sun reaches 15 million Kelvin. The surface of the hottest known stars barely exceeds 50,000 Kelvin. The corona of Maxi J1820 plus 070 was burning at temperatures 66 times hotter than the sun's core, hot enough to strip electrons from iron nuclei and create a plasma state so energetic that quantum effects begin to dominate classical physics. Simultaneously, the Very Long Baseline Array radio telescopes detected the jets. Matter was being launched from the vicinity of the black hole's event horizon at 240,000 kilometers per second, 80% the speed of light. In twin beams so perfectly collimated, they maintained their structure across distances measured in light years. The high-energy stereoscopic system telescopes in Namibia confirmed that these jets were accelerating particles to energies exceeding 100 tera-electron volts, energies that rival the most powerful particle accelerators ever built by human civilization. Dr. Mariko Kimura and her team at the Institute of Space and Astronautical Science published their analysis in Nature Astronomy in 2019. The observations revealed that the corona and the jets were not independent phenomena, but part of a single, coherent system where the billion-degree plasma was somehow feeding the relativistic jets while maintaining thermal equilibrium across temperature gradients that should have caused immediate thermal runaway or collapse. The standard cosmological model says that accretion disk coronae form when magnetic field lines above a black hole reconnect violently, heating plasma through magnetic reconnection events similar to solar flares, but scaled up by factors of millions. The jets emerge through the Blandford-Zoniac mechanism, where the black hole's rotation extracts energy from its ergosphere and channels it along magnetic field lines that thread the event horizon. These processes should be coupled but chaotic, with corona temperatures varying wildly as magnetic field configurations shift and reconnect in unpredictable patterns. But MAXI J1820 plus 070 maintain its billion-degree corona temperature with remarkable stability while simultaneously powering jets at constant velocities for weeks. The European Southern Observatory's Very Large Telescope Interferometer tracked the system through multiple orbital periods and found that the corona temperature remained within 2% of 1 billion Kelvin, despite the complex dance of matter spiraling into the black hole's gravitational well. The jets maintained their 80% light-speed velocities with similar precision, as if some mechanism were actively regulating both the thermal and kinetic energy output. Radio observations by the Atacama Large Millimeter Array revealed even stranger behavior. The jets were not continuous streams, but consisted of discrete plasma bullets launched at regular intervals, each bullet containing approximately 10 to the 32nd power particles accelerated to identical velocities. The timing was so precise that astronomers could predict when the next plasma bullet would be launched to within seconds, despite the chaotic environment of the accretion disk from which they originated. Some astrophysicists suggest that MAXI J1820 plus 070 represents a previously unknown phase transition in black hole accretion physics, where the interplay between magnetic fields, plasma dynamics, and space-time curvature creates a self-regulating system that maintains thermal and kinetic equilibrium. Others propose that the black hole's spin and magnetic field configuration have achieved a resonant state that allows for unprecedented efficiency in converting gravitational potential energy into both thermal and kinetic energy simultaneously. How does a chaotic system like an accretion disk maintain billion-degree temperatures with clockwork precision? What mechanism synchronizes corona heating with jet launching across distances where light itself takes hours to travel? Why do the plasma bullets carry identical energy loads despite emerging from a turbulent environment where no two magnetic reconnection events should be the same? Can the laws of thermodynamics accommodate a system that appears to violate the principle that entropy must increase in isolated systems? The universe contains black holes that operate with the precision of atomic clocks while generating conditions more extreme than the Big Bang itself. And MAXI J1820 plus 070 is teaching us that some cosmic engines run by rules we have yet to discover. 4U1000, 630 to 47. You are watching the Rossi X-ray Timing Explorer's data stream cascade across your monitor at the Goddard Space Flight Center, and something is fundamentally wrong with the physics. The X-ray signature from this stellar black hole, 4,000 light-years away in the constellation Norma, isn't behaving like any theoretical model predicts. The spectral lines are Doppler shifted so violently that the ionized iron atoms are moving at 30,000 kilometers per second, 10% the speed of light, directly away from the black hole. This is matter that should be falling inward, spiraling to its doom past the event horizon. Instead, it's being launched into space with the kinetic energy of a stellar explosion. The Chandra X-ray Observatory confirmed what Rossi first detected in 1998 when astronomer Michael Garcia and his team at the Harvard-Smithsonian Center for Astrophysics published their findings in the Astrophysical Journal. This black hole, designated 4U1630 to 47, possesses a mass roughly 10 times that of our Sun and orbits, with a companion star in a binary system. The companion feeds material onto an accretion disk that should heat to millions of degrees Kelvin as it spirals inward, generating the characteristic X-ray emissions we observe. But the European Space Agency's XMM Newton telescope revealed something that challenges the fundamental physics of accretion. Winds of ionized gas streaming away from the black hole at velocities that approach relativistic speeds. Dr. John Miller of the University of Michigan and his international team used a nuclear spectroscopic telescope array to map these winds in unprecedented detail. Their 2014 study measured outflow velocities of 30,000 kilometers per second, fast enough to travel from Earth to the moon in 13 seconds. The winds carry ionized iron, oxygen, and neon, elements heated to temperatures exceeding 10 million degrees Kelvin. Most disturbing of all, these winds are carrying away more mass than the black hole is actually consuming from its companion star. Here's what makes this impossible. Black holes are defined by their gravitational dominance. Nothing with mass can escape once it crosses the event horizon. Even outside the event horizon, the mathematics of general relativity describe how matter should behave near a black hole. It forms an accretion disk, heats up through friction and magnetic forces, and eventually crosses the point of no return. The energy released as matter falls inward powers the X-ray emissions we observe. This is accretion physics, tested and confirmed across thousands of black hole systems throughout the galaxy. The standard cosmological model says that stellar black holes, like 4U 630 to 47, should be efficient matter processors. The accretion disk converts gravitational potential energy into thermal and kinetic energy with an efficiency that exceeds nuclear fusion. Some material might be ejected in narrow jets along the rotation axis, but these jets typically carry away less than 10% of the infalling matter. The bulk of the material should cross the event horizon and disappear from our observable universe forever. But the data from multiple X-ray observatories tells a different story. These winds from 4U 630 to 47 are not narrow jets confined to the rotation axis. They are broad, spherical outflows that encompass nearly the entire accretion disk. The velocities measured by the Doppler shifts of ionized iron lines indicate that the material is being accelerated by forces more powerful than the black hole's gravitational pull at those distances. Ashley King of Stanford University calculated that the kinetic energy carried by these winds exceeds the binding energy of the accretion disk by factors of 10 or more. Some astrophysicists suggest that intense magnetic fields generated within the accretion disk could launch these winds through magnetohydrodynamic processes. The rotation of the black hole might drag space-time itself, creating a dynamo effect that amplifies magnetic fields to strengths trillions of times greater than Earth's magnetic field. These fields could, in theory, accelerate ionized particles to the observed velocities through magnetic pressure and reconnection events. Others propose that radiation pressure from the X-rays generated near the event horizon could drive these winds. If the accretion rate becomes super Eddington, exceeding the theoretical limit at which radiation pressure should halt further accretion, the intense X-ray flux might blow away the outer layers of the accretion disk. But this explanation requires luminosities that 4U 630 to 47 simply doesn't display. What force can accelerate matter to 30,000 kilometers per second against the gravitational pull of a 10 solar mass black hole? How can an object, defined by its ability to capture matter, instead expel more mass than it consumes? Why do the magnetic field strengths required for these wind speeds exceed what magnetohydrodynamic theory predicts for stellar black holes? If black holes can lose more matter than they gain, what does this mean for their growth and evolution across cosmic time? How many other black holes are defying accretion physics in ways we haven't yet detected? But 4U 630 to 47 represents just one black hole behaving impossibly elsewhere in the cosmos. An even stranger system challenges our understanding of what black holes can do to the fabric of space-time itself. OJ 287. You are staring at a computer screen in the Lowell Observatory in Flagstaff, Arizona on March 23, 2008. The numbers refuse to make sense. Light curve after light curve, stretching back 120 years of astronomical observations, all telling the same impossible story. Every 12 years, like clockwork, a distant galaxy flares. Not a gradual brightening, not a random burst. A precise, predictable outburst that follows orbital mechanics with the regularity of a Swiss timepiece. The galaxy is 3.5 billion light years away. You are watching two supermassive black holes dancing with each other. The Spitzer Space Telescope first confirmed what optical telescopes had been recording since 1891. OJ 287, a blazar in the constellation Cancer, contains not one but two supermassive black holes locked in a death spiral. The primary black hole weighs 18 billion times our sun's mass. Its companion weighs 150 million solar masses. They orbit each other every 12.2 years at a distance of 130 billion kilometers. For perspective, that is closer than Neptune orbits our sun. Here's what makes this impossible. Two supermassive black holes, this massive, should have merged billions of years ago. When objects of this scale orbit at these distances, they radiate gravitational waves that steal energy from their orbit, causing them to spiral inward. Einstein's general relativity predicts they should have collided within 10 million years of forming this binary system. Yet OJ287 has maintained its 12-year orbital period for over a century of human observations, suggesting this dance has continued for hundreds of millions of years. The Kepler Space Telescope and the Transiting Exoplanet Survey satellite have tracked the system's brightness variations with unprecedented precision. Every 12 years, the smaller black hole plunges through the accretion disk of the larger one, heating gas at temperatures exceeding 1 billion Kelvin and producing an outburst visible across 3.5 billion light-years of space. The energy released in each outburst equals the total luminosity of 1 trillion suns. The regularity is so precise that astronomers successfully predicted the 2007 outburst to within 3 weeks and the 2019 event to within 1 month. The gravitational wave detector networks, the Laser Interferometer Gravitational Wave Observatory in Virgo, should theoretically detect waves from this system. At these masses and orbital distances, OJ287 should be radiating gravitational waves with an amplitude detectable from Earth. The waves should carry away orbital energy at a rate that would cause the black holes to spiral inward measurably over human timescales. Teams led by Mauri Valtonen at the University of Turku have calculated that the orbit should decay by 11 minutes per orbital period due to gravitational wave emission. The standard cosmological model says this system represents the final stage of galactic merger evolution. When galaxies collide, their central supermassive black holes eventually form binaries that radiate gravitational waves and merge within cosmologically short timeframes. Computer simulations by researchers at the Max Planck Institute for Gravitational Physics show that supermassive black hole binaries at these separations should merge rapidly, contributing to the gravitational wave background detectable by current instruments. But the observations tell a different story. The orbital period of OJ287 has remained constant within measurement error for over 130 years of recorded observations. No detectable orbital decay, no measurable increase in outburst frequency. The system appears locked in a stable configuration that defies our understanding of gravitational wave emission from massive binaries. Observations by the Very Long Baseline Array Radio Telescope network show no evidence of the rapid in-spiral predicted by general relativity. Some astrophysicists suggest the binary exists in a region of parameter space where three-body effects dominate. Perhaps a third supermassive black hole, undetected at the system's center of mass, provides gravitational perturbations that stabilize the orbit against decay. Others propose that magnetic field interactions between the black hole's ergospheres create forces that counteract gravitational wave energy loss. A minority of researchers have suggested modifications to general relativity itself might be necessary to explain the system's stability. The European Space Agency's Laser Interferometer Space Antenna mission, scheduled for launch in 2037, will have the sensitivity to detect gravitational waves from OJ287 if they exist at predicted amplitudes. Current non-detections by ground-based observatories either indicate the waves are below theoretical predictions or propagate differently than Einstein's field equations suggest. How do two supermassive black holes maintain a stable 12-year orbit when physics says they should merge? Why do gravitational wave detectors remain silent when theory predicts a detectable signal? What mechanism prevents these cosmic monsters from completing their inevitable spiral into each other? Is OJ287 revealing gaps in our understanding of space-time itself? But even stable systems can hide sudden transformations, as one galaxy's dying central engine demonstrates. IC 3599. You are staring at a galaxy that has been dead for millions of years. The Wide Field Camera 3 aboard the Hubble Space Telescope has been tracking IC 3,599 inches, the constellation Ursa Major, for decades. 150 million light-years away, this spiral galaxy drifts through space, with a cosmic equivalent of a corpse at its center. Its supermassive black hole, 4 million times the mass of our Sun, sits dormant. No accretion disk, no jets of superheated plasma, no X-ray emissions, nothing. For as long as humans have been watching, this galactic heart has been utterly, completely silent. Then, on December 14th, 2010, IC 3,599 screams. The Galaxy Evolution Explorer satellite detects the first anomaly, a sudden spike in ultraviolet radiation coming from the galaxy's nucleus. Within hours, ground-based observatories around the world confirm what seems impossible. IC 3,599's supermassive black hole is erupting with the fury of a quasar, blasting jets of ionized matter across hundreds of thousands of light-years. The Chandra X-ray Observatory registers emissions climbing to 10 to the 43rd ergs per second. The Very Large Array in New Mexico tracks massive radio lobes expanding outward from the galactic core at nearly 20% the speed of light. Dr. Rebecca Canning and her team at the University of Cambridge published their analysis in the Astrophysical Journal in 2011, documenting what they term an unprecedented reactivation event. The dormant supermassive black hole in IC 3,599 has transformed from cosmic silence to one of the most luminous objects in the local universe. Group. The energy output exceeds that of 100 billion suns. Material is being accelerated to relativistic speeds and ejected in twin jets that stretch across 400,000 light-years, nearly 4 times the diameter of the Milky Way. Here's what makes this impossible. Supermassive black holes don't just wake up. They feed when matter falls into their gravitational wells, forming accretion disks that heat to millions of degrees Kelvin and generate the spectacular light shows we observe as quasars and active galactic nuclei. But the Hubble Space Telescope's deep field observations of IC 3,599 reveal no obvious fuel source, no recent galaxy mergers, no disrupted star formation regions, no tidal streams of gas being pulled into the nucleus. The galaxy appears structurally undisturbed, its spiral arms intact, its stellar populations aging peacefully in their orbits. The mainstream scientific consensus explains sudden black hole activation through disruption events. A massive star wanders too close to the supermassive black hole and gets torn apart by tidal forces, providing fresh material to restart the feeding process. Or a galaxy collision funnels gas toward the central engine, reigniting dormant activity. The Standard Model requires fuel something with mass and angular momentum that can form an accretion disk and generate the observed emissions through gravitational conversion of potential energy to radiation. But the observations of IC 3,599 don't support this explanation. Follow-up surveys with the Spitzer Space Telescope reveal no infrared signatures of disrupted stellar material. The Atacama Large Millimeter Array detects no molecular gas clouds streaming toward the galactic center. Radio observations show no evidence of recent interactions with neighboring galaxies. The supermassive black hole appears to have activated without consuming anything detectable. It's generating the energy output of 100 billion stars while apparently feeding on empty space. Some astrophysicists suggest the activation represents the delayed aftermath of a galaxy merger that occurred hundreds of millions of years ago, with material finally reaching the black hole after a complex orbital decay. Others propose that dark matter interactions might provide an undetectable fuel source, or that magnetic field reconnection events in the accretion disk remnants could trigger sudden reactivation. A minority of researchers have suggested that supermassive black holes might harbor internal energy sources, mechanisms that allow them to generate luminosity without external matter input. The European Space Agency's XMM Newton Observatory continues monitoring IC 3,599, documenting how its emissions fluctuate across multiple wavelengths. The black hole's activity remains high 7 years after the initial outburst, suggesting this isn't a brief flare, but a sustained reactivation. Yet no theoretical model adequately explains how a 4 million solar mass black hole maintains such extreme luminosity without visible fuel consumption. The energy has to come from somewhere. Conservation of energy doesn't allow exceptions, even for supermassive black holes. What triggers a cosmic engine that has been dormant for millions of years? How does a supermassive black hole generate the luminosity of 100 billion stars without consuming detectable matter? Can black holes access energy sources that exist beyond our current understanding of physics? What does it mean when the universe's most massive objects can apparently violate our fundamental assumptions about how they operate? As we reach the end of our journey through these 10 cosmic impossibilities, one pattern emerges with disturbing clarity. The pattern emerges from the darkness. 10 black holes, each one breaking our models in a different way. Sagittarius A star, spinning impossibly fast at the center of everything we know. Ton, 618, consuming matter at rates that should collapse the physics of accretion. GW 150914, merging in ways that suggest the universe has been hiding entire populations of massive objects. M87 star, launching jets that carve through space-time itself. XTE J1550 564, flickering with X-ray patterns that reveal the quantum mechanics of event horizons. Swift J, 1644 plus 57, tearing apart stars with tidal forces that reach across light years. Maxi J, 1820 plus 070, switching between accretion states like a cosmic light switch. 4U, 1630 to 47, generating winds that should not exist. OJ, 287, orbiting in a binary system that defies every prediction. IC, 3599, awakening from dormancy to consume galaxies. Each discovery forces the same uncomfortable conclusion. Our cosmological models are not wrong, they are incomplete. The universe operates on scales and through mechanisms that our current framework cannot accommodate. We have built equations that work beautifully for the small sample of space-time we can observe directly. But these 10 objects exist in regimes where mass bends space-time beyond recognition, where magnetic fields achieve strengths that make laboratory physics irrelevant, where gravity becomes so extreme that matter behaves in ways we have never seen. They are not anomalies. They are glimpses of a deeper reality that our models cannot yet reach. The most unsettling possibility is that these black holes are not exotic exceptions scattered through an otherwise comprehensible universe. They are the universe showing us what it actually is when the constraints of human observation are removed. Every galaxy harbors objects like these. Every region of space operates according to physics we have not discovered. The cosmos we think we understand, built from stars that burn predictably, and galaxies that rotate, according to Newton's laws, may be the aberration. The real universe may be the one these black holes inhabit, strange, violent, and utterly indifferent to the small corner of space-time where human consciousness emerged to ask questions about the darkness that surrounds it.